Let us talk about the last bit of this chapter, that is oblique collision. In oblique collision, as I defined, as a collision when the body line of motion differs from the line of impact. If you take the example of this ball which hit the ground, smooth ground, either the ground is smooth or the ball is smooth, thing will be same. This ball will get a reaction force along the normal direction because the ball is smooth or ground is smooth, or both can be smooth. Only normal reaction will come into play, and if both the surfaces are rough, if one surface is rough, other is smooth, no friction will come into play because frictional force is a tangential contact force. The frictional force prevails along the tangent. The frictional force prevails along the tangent, and frictional force will be 0 if the bodies are smooth, or at least one body is smooth. This is the idea. So, oblique collision, the assumption is smooth surface. If the surfaces or one of the surface or one of the body is smooth, the impact force is always normal in this case. So, this is the impulse of the impact force. Since collision takes place along this line, along the normal, this is called line of collision. Line of collision, line of motion are two different lines. Therefore, this collision is called oblique collision. When I started the chapter, I talked about the definition of oblique collision, that in oblique collision, the line of motion and the line of impact do not coincide. For instance, the ball collides at an angle of theta with respect to vertical with a velocity, suppose v0. And just after the collision, let the ball get away or bounce back with the velocity v at an angle phi with respect to the vertical. Result the velocity along the tangent and along the normal. Along the normal, the velocity component is v sin theta, v cos phi, because you have taken phi with respect to the normal. If you take phi with respect to the horizontal, this will be v sin theta. And the tangential component of the velocity will be v sin phi. Since or if the surfaces either are smooth, frictional force will vanish. Therefore, net force is vertical during the collision. that is n minus mg. This means that net force along x direction or tangential direction is always 0 under this condition. Net force along x direction is 0. Hence, we can conserve the momentum of the object if you take this as the system of the single particle. The system's momentum along x direction must be conserved. Its momentum along x direction is equal to m into the velocity of the object along x direction remains conserved. Therefore, the x component of the velocity of the object should be equated just before and just after the collision, or is conserved. In this problem, what is the x component of the velocity just before the collision? V naught sin theta, and y component, a vertical component, V naught cos theta. These are the components of the velocity just before, just after the collision. Well, Newton's empirical formula says that the approach velocity into minus a equal to separation velocity. Approach velocity is the velocity along the line of impact between these two bodies. The ground is one body, this is at rest, this is one body. So, approach velocity is equal to, if you take this is 1, this is 2, you can write u1 y minus u2 y. This is approach velocity, and separation velocity v1 y minus v2 y. Y means vertical direction or y axis into E. Since the ground is at rest, it is not moving, this will be 0. Since the body 2 moves down with a velocity v naught cos theta, it will be minus v naught cos theta. This point 1 does not move, therefore, its velocity just after the collision along y direction is 0. And this body just after the collision, and this is just before collision. Just after collision, if you take the velocity in this direction, its y component is upward, that's positive, v cos phi. So, this gives us v cos phi is equal to E v naught cos theta. This is equation number 1. Or you can call it equation number 2, because from this momentum conservation equation, we can write that x component of the momentum of the body just before the collision, that's equal to v naught sin theta into its mass is equal to x component of the momentum or the velocity of the object just after the collision, that is mv sin phi. Momentum or velocity, anyone you can conserve, both the quantities can be conserved. So this is equation 1, this is equation 2, and we have two unknown quantities V and phi. Unknown quantities, we need them, and we have two equations, two unknown quantities, very easily we can solve. So how to solve? Let us see. Rewrite the equations. V sin phi equal to V naught sin theta, and V cos phi is equal to A V naught cos theta. Let us solve these two equations. Just divide equation 1 by equation 2, equation 1 with equation 2. This V will be getting cancelled, V naught will be getting cancelled. So we are getting tan phi is equal to tan theta upon E. This gives us the direction of motion of the object just after the collision is equal to tan inverse tan theta upon E. And if you square these two equations and add them, we are getting V square is equal to V naught square sin square theta plus A square cos square theta. And this gives us the velocity of the speed of the object just after the collision, that's equal to V naught into square root of sin square theta plus A square cos square theta. And how much energy is lost also you can calculate. The energy lost is equal to change in kinetic energy, half m V square minus half m V naught square. Half m, take common, what is V square? V naught square sin square theta plus A square V naught square cos square theta minus V naught square. This gives us m by 2 V naught square sin square theta minus 1 plus A square cos square theta, and this is equal to minus cos square theta. So you can just write m V naught square cos square theta into 1 minus A square. You can say that in this collision, the momentum along the x direction remains conserved. Therefore, the kinetic energy along the x direction remains conserved. So, which kinetic energy is changing? Kinetic energy along y direction is changing. In that way also you can write the heat loss to the energy loss is equal to kinetic energy along y direction final minus kinetic energy along y direction initial. So we can just write half m Vy square minus half m Uy square. You take half m common, Vy equal to E into Uy. This gives us half m, take the mod of m Uy square 1 minus A square, and Uy equal to B naught cos theta square of this 1 minus c square, and this is the answer you obtained previously by using the basic principles. Using the concept also you can get same answer, that along the x direction the velocity, the kinetic energy of the object remains conserved. In this way we can get the idea, the basic idea of oblique collision. Of course, in further classes we can extend the ideas in solving more problems. In rigid body also we can extend this concept of oblique collision and eccentric collision, etc., collision of the particles with the rigid bodies. Thanks all of you.